All right, let's get right into it. We're about to pull back the curtain on one of the coolest, most fundamental ideas in all of computing. We're talking about the fork system call, and we're going to figure out how a single program can perform a bit of magic and split itself in two.
I mean, have you ever really stopped to think about it? When you type a command into your terminal, how does the terminal itself not just freeze up while your command is running? Or how does a web server handle thousands of people all clicking at the exact same time? Well, the secret starts with a single process learning how to clone itself.
So, that's where we're going to start. Let's think of fork as a kind of digital cloning machine. It's a way for a running program to create a perfect, instantaneous duplicate of itself.
So what exactly is forking? Well, it's a system call, and that's just a fancy way of saying it's a program raising its hand and asking the operating system, the boss, to do something special. In this case, the request is incredibly simple, but also incredibly powerful. Clone me right now.
And this visual right here shows it perfectly. On the left, before the fork call, you've just got one process, the parent. Then it makes the call and boom, suddenly there are two. The original parent is still there, but now it has a brand new identical child process running alongside it.
So here's the really crucial part. The child isn't just some blank new program. Nope, it's an exact copy of the parent at that very moment. And they both start running at the same time, picking up from the exact same spot the very next line of code after fork was called. It's almost like the program's timeline just split into two parallel universes.
Okay, but wait. This brings up a really interesting problem, right? If the child is a perfect clone of the parent, how does it know it's the child? And how does the parent know it's the parent? Well, the answer is just brilliant, and it lies in what we're calling the secret return value.
This is the absolute key to making fork useful. Without some way for them to tell each other apart, they would just do the exact same thing forever. And we need them to be able to take on different jobs.
And the solution is so elegant. The fork system call actually gives back a number. But here's the trick. It gives a different number to each process. The child process gets back a 0. That's its signal. Hey, you're the new kid. But the parent process, it gets back a positive number, which is the unique ID of its new child. It's like the system hands the parent a birth certificate. And of course, if it returns -1, well, something went wrong.
And this is what it looks like in actual code. This little structure is the heart of multitasking. You call forking, you store that return value, and then you use a simple if-else check. It is literally a fork in the road for your program.
So let's just nail this down one more time. First, fork happens. The clone is made. The child gets a return value of 0, so the if condition is true, and it runs the code in the if block. The parent gets a positive number, its new child's ID, so the condition is false, and it skips right over to the else block. Simple as that, but so powerful.
All right, so one process becomes two. That makes sense. But what happens if the clones start cloning themselves? This is where things get really, really interesting, and you start to see the true power here.
So let's just think about it. Imagine you have a line of code that says fork, and then right below it, another line that says fork. When all the dust settles, how many total processes do you think we have? You might think 3, right? The original plus the 2 new ones it created? Nope. The answer is 4. It might not be intuitive at first, but it follows a perfect logical pattern. Let's trace this out on the diagram, because it's pretty cool. The original process, P0, hits the first fork call. Bam, it creates P1. Now we have 2 processes running. And here's the catch. Both of them keep executing and hit the second fork call. So the original P0 forks again and creates P2. But at the same time, the child P1 also forks and it creates P3. 1 becomes 2, and then those 2 each become 2 more. Total, 4. This exponential growth gives us a beautiful, simple rule of thumb. It's the 2 to the n rule. If you call fork n times, you end up with 2 to the power of n total processes. So 3 fork calls get you 8 processes. 4 calls get you 16. It's a process explosion, literally.
Okay, so you've got this explosion of processes running all at once, but that can get messy. The operating system doesn't make any promises about which one runs first or finishes first. It's basically a free-for-all. So how do we bring some order to this chaos and manage the family?
Without any kind of control, the output of your program can be totally unpredictable. The parent might finish its work before the child even starts, or the child might finish first. You just never know. This is a classic race condition, but thankfully, we have a tool to manage the race.
And that tool is another system call called wait, and it does exactly what you think it does.
The parent process can call wait, and it essentially just pauses itself. It says, okay, I'm going to stop right here, and I'm not doing anything else until my child has finished its job. It's like the parent waiting for the kid to finish their chores. It brings predictability back into the picture.
All right, so this has all been really cool theory, but why does any of this actually matter to you? Right now, using your computer, let's connect the dots from this abstract idea to your everyday experience.
Now, here's a super important distinction. Fork just makes a clone. The clone runs the same program. If you want that clone to do a totally different job, like run a different application, you need a partner in crime, another command called exec. This two-step dance of fork, then exec, is one of the most fundamental patterns in all of modern operating systems.
And once you know about this pattern, you see it everywhere. Every single time you type ls or grep in your terminal, your shell forks and the child execs to become that command. A giant web server handling thousands of users, it's forking off little child processes to handle each person's request. Even your web browser, it forks new processes for your tabs, which is why when one tab crashes, it doesn't take your whole browser down with it. It's the building block of everything.
So the next time you open a browser tab or run a command, you'll know the secret. You'll know there's a little fork call happening under the hood, creating a clone, and using a clever return value to chart a new path. It's the foundation of the massive parallel world that makes our computers so powerful. Now that you've seen how programs are born, it kind of makes you wonder, what other elegant secrets are running on your machine right now? Thanks for diving in with me on this explainer.